In today's lecture, we're going to look at the mode structure of the rectangular waveguide. In the previous two lectures, in lecture 9a, we developed the expressions that allow us to compute the E sub x, E sub y, H sub x, and H sub y, the transverse components of the E and H fields, in terms of the longitudinal components, E sub z and H sub z. And in lecture 9, we then did separation of variables on those longitudinal components in order to define the TE and TM modes. What we're going to do now is we're going to look at how those equations relate to physical mode structures inside the waveguide, specifically for rectangular waveguides, since that's the most important type of waveguide that you're going to be dealing with. There are two primary learning objectives. The first is to learn the shape and the nature of the modes on a rectangular waveguide. So you should be familiar with the first few TE and TM modes and the distribution of the fields. And you should be able to relate the geometrical field distribution to the mathematical relationships that you can develop from doing the Helmholtz equation. You might ask why this is important. Well, it's important because one of the real difficult things in dealing with waveguide circuits is when you need to go from one type of waveguide to another type of waveguide. So for example, in lab number 2, you're going to go from coaxial waveguide into rectangular waveguide. And whenever you make those transitions, you have to find a way to make the two geometries look enough like each other so that the mode coming in can excite the mode going out. And you'll see an example of that when you do your laboratory number 2. And this is a common theme that comes into play when you're dealing with microwave circuits. The second learning objective is to look at the dispersion relationship for the first few modes for rectangular waveguide. So you should be able to analyze the mode propagation properties from the dispersion diagram, and you need to understand what those cutoff frequencies are and where you're going to operate a waveguide in any particular circumstance. In the previous lecture, we did the separation of variables in order for us to be able to come up with a solution to the Helmholtz equation for the TE and the TM modes. And what we did is we noted that I don't have to solve for E sub x, E sub y, H sub x, and H sub y, because I can write them in terms of E sub z and H sub z. And if I then solve for the two longitudinal components, I can compute the other 4 components. We then expand those two functions in terms of the Helmholtz equation, and we apply the boundary conditions on the perfect electrical conducting interfaces of the waveguide walls. And the boundary conditions that we used was that the normal component of the magnetic field was equal to 0. We could have used that the tangential component of the electric field was equal to 0, but we chose to use the normal component. So at x equals 0, and x equals a, I've got the normal component of the magnetic field being the h sub x, and that h sub x is equal to 0 at the left and right walls. Likewise, I've got at the top and bottom walls, I've got h sub y equal to 0, as we see here. Right? And going through those formulas allowed us to come up with a mode distribution. So we solved initially for the z component of the magnetic field, and the z component of the magnetic field for the TE modes, this is for the TE modes, took this structure. So we have some coefficient out in front. Some students asked me about the coefficient in one of the previous lectures. This is just a mode coefficient that tells how strong the mode is in any particular problem. It doesn't change the shape of the mode. And this is going to vary based upon the power of your transmitter, or if you're using it as an antenna, the power of the signal coming in. It's going to go up and down, and that means the waveguide is going to be carrying more or less power. The amount of power that the waveguide is carrying is going to be proportional to A, but it doesn't change the nature of the mode. We see that we've got cosine m pi x, right, and m pi over a in the x direction, and n pi over b times y in the y direction. And of course we have our propagation term, our propagation constant, where we've got e to the minus j beta sub z times z. Right? So let's take a look at what happens when we evaluate each of these 5 functions for a few of the modes. So we'll start off with the lowest order mode, or the dominant mode, and recall the dominant mode, or not recall, the dominant mode is the one that has the lowest cutoff frequency. And we know, we know that the cutoff frequency is given by f sub c equals the square root of omega squared mu epsilon Okay? Then we're going to subtract off these terms. So I've got minus, let's see, m pi over a squared minus n pi over b squared. Right? So there's my cutoff frequency. Now, the lowest cutoff frequency would be at m equals 0 and n equals 0, but that would correspond to a TEM mode, and we don't have the TEM mode in this waveguide. So the next lowest mode will be the one where the sum of these two terms is as small as possible. Since A is larger than B in our waveguide, that will be when m equals 1 and n equals 0. Right? So the lowest order mode, or the dominant mode, is when m equals 1 and n equals 0. So if I come over here, n equals 0 makes this go away. Right? N equals 0 makes this entire term go away. N equals 0 makes this entire term go away. Right? So we're doing n equals 0. Right? And m equals 1, then n equals 0 makes this term go to 1, and this term go to 1. Okay? And when I have the m equals 1 come into play, I've got cosine pi x over a for the z component, sine pi x over a for the y component, and the y component of E and the x component of H. So let's see what that ends up doing when we look at the mode structure. So what we're plotting here is the amplitude of each of the 6 field components for this particular mode, and this is the TE10 mode. We've got the x direction here, the y direction going in and out of the plane, and the z direction, direction of propagation, and this is frozen at one instant of time. And what we can see is that if I move in the y direction at any given position x and z, the fields are constant. And that corresponds with what we see here, because m is equal to 0, n is equal to 0, so I've got this constant term here. Right? No variability in the y component. So if n equals 0, this term goes to 1, this is no longer a function of y. And we see that borne out in all of the fields. We see that I've got a y component of my electric field and an x component of my magnetic field. Right? And if I move in the x direction, right? Let's say I move here through the middle where the fields are the strongest. I have a peak in the middle, and then that rolls off and goes to 0 at the edges. Well, that makes sense because I've got the sine pi x over a. So for x equals 0, this goes to 0. For x equals a, this goes to 0. And in between, I've got half a cycle of a sine wave. When I move up to the 1-1 mode, so this is the TE11 mode, right? We now would expect to have cosine pi x over a, cosine pi y over b for our variability in the z-axis, and we have 1/2 cycle of a sine wave in each direction for each term. Right? And we can see that here, for example, with e sub y. If I move from one side to the other, I have a minimum, go to a maximum, and back to a minimum. Right? So that's a 1/2 cycle of the sine wave. If I move in the y direction, I go from -1 through a 0 to +1. Right? So I've got 1/2 cycle of the sine in both directions of the field. When I go to the 2-0 mode, what the 2-0 mode means is now I've got cosine 2 pi x over a and sine of 0, because that's not going to look at, right? Sine of 2 pi x over a, cosine of 0. So I'm going to get one full cycle of a sine wave in the x direction and no variability in the y direction, and we see that borne out. I get a 0 to a maximum, back to 0 to a minimum, and back to 0 when I move in the x direction, and in the y direction things are constant. And I can go to the higher order modes to take a look at that. Likewise for the TM modes have the z component of h equal to 0. But I can solve for the z component of the electric field, but now instead of having cosine times cosine, I've got sine times sine variability. Here are my terms that fall out of the expression when I plug E sub z into my waveguide field equations, and all these things. Now, one thing we note is that when m and n are both equal to 0, the z component of the electric field is equal to 0, and the mode is equal to 0. Right? Because when m and n are both equal to 0, all of these terms go away. So the lowest order TM mode is the TM11 mode. Okay? So take a look at what that mode looks like. The TM11 mode has this sort of behavior. We see again we have a half cycle of a sine wave in the x direction, and I go from +1 through a 0 to -1, or probably -1 through 0 to +1 in the y direction. So I've got half a cycle of a sine wave in both directions. I'm going to show you plots in a moment using CST Microwave Studio that visualize this in a different way that may be easier for you to see. When I step up in mode numbers, okay, there are no fields for the TM20 mode because I have sine of 0, but the TM21 mode has a full cycle, 2 half cycles of a sine wave in the x direction, and 1 half cycle of a sine wave in the y direction. The last thing I want to look at in this slide set before I go over to CST Microwave Studio is look at the dispersion diagram. What we're plotting here is the omega versus beta, or in this case Andre's plotted the frequency versus beta for different mode indices. And going back to what I said previously, the cutoff frequency, we have different cutoff frequencies for each of these modes, and since the cutoff frequency depends upon the m and the n the same way for both TE and TM modes, then I've got the same cutoff frequencies for TE and TM modes that have the same indices. Now, for these two, the 1,0 and 2,0 modes, I have a TE mode only. But for these two, I've got both TE and TM modes. And these aren't all the modes. There's also a 0,1 mode and a 0,2 mode that would fit into this picture as well. But we see that the lowest cutoff frequency is here, and it corresponds to the TE10 mode. And then there's the TE20 mode, which has a higher cutoff frequency. The TM and TE11 modes have a slightly higher cutoff frequency. The TE and TM21 modes have a slightly higher cutoff frequency. And from this plot, I can get the phase and the group velocity. Just to remind us, the phase velocity is given by the slope of this line. Okay, so the phase velocity is equal to omega over beta. And the group velocity is given by the slope of the dispersion diagram. So the slope of that line gives me u sub g, or d omega d beta. So now in order to illustrate this a little bit differently, what I'm going to do is I'm going to pull up CST Microwave Studio, and we're going to take a look at the solutions to the waveguide equation. To the Helmholtz equation done numerically. Okay, so now what I have open is CST Microwave Studio, and in CST Microwave Studio here you can see that I've got a waveguide built. This is similar to the one that I built in class on Tuesday. If I come in here and I take a look at the View menu, and I'll do a X cutting plane, you can see that the waveguide is hollow. I've got it filled with vacuum. Let's see, I'm gonna do some measurements here. We'll pick some points and we'll see the separation. So I've got a point here and here, and we see those points. The distance there is 2 centimeters. I'll turn the cutting plane off, pick another point, and well, let's clear that. Let's pick one point and pick another point, and we see that the inside dimension is 4. So this waveguide is 2 centimeters in height, 4 centimeters in width. And that corresponds to the values that Andre used when he computed this plot. Right? So A was 4 centimeters, B was 2 centimeters, and we see that there's a cutoff frequency somewhere around 4 gigahertz is what we expect to find for the lowest order mode when we look at the cutoff frequencies. As I indicated, what we have here is the 1.0, the 2.0, the 1.1, the 2.1. There's also a 0.1 mode, and the 0.0 mode we'll see will slide in between here. So going back to CST, I've already run the simulation, and when I ran the simulation, you'll see that I had the ports set up to run the first 7 modes. So both port 1 and port 2 had 7 modes that were computed for it. And when I ran the simulation, I only simulated exciting port 1 just to save the time on the simulation. And we get a whole series of results. So the first thing I'm going to do is I'm going to take a look at the port mode fields. Right, so we'll come in here, we'll take a look at the 2D results, port modes, port 1, and we'll take a look at the dominant mode, or the lowest order mode, what we know to be the TE10 mode. And we see exactly what the equations predicted we were going to see. We see an electric field which is only in the y direction, right here's y, and that field is maximum in the center, and it falls off like a cosine as it goes side to side. There's no variability, though, in the y direction. And when we go back to our field equations for the 1,0 mode, here's our field equations, and we see that for the 1,0 mode, I've got e sub y varies like sine pi x over a, so it's 0 at x equals 0, it's 0 at x equals a, and it's maximum at x equals a over 2. There's no variability in the y direction. So I've got the E fields for the port mode. The H fields have exactly the same variability, but they're in the x direction. So when we take a look at the H fields for the first mode, we see exactly the same field distribution. Okay. And when I come in here and I take a look at the electric fields that I simulated, I can take a look at the electric fields at a frequency of 10 gigahertz, and it asks me which mode I want to take a look at. So I'm going to take a look at the lowest order mode. And I'm going to take a look, turning this so I can look at the fields in general. Take a look on a 2D plane, but I'm going to change my plane here to an x-axis. All right. I picked y. I meant to pick x. There we go. All right, so here are my fields, and I'm going to allow these fields to animate. And we can see that I have this mode propagating down the line. Right, so the field goes from positive to negative to positive to negative. Allow it to propagate, and this signal just moves right on down the line, as we would have expected it to do based upon what we know about the mode. And I can also take a look at the surface current that supports this mode. So I'll come down here, I'll take a look at the surface current for that lowest order mode, and we can see that I've got currents on the top, bottom, and sides, and I allow them to propagate, and we see that those currents oscillate as they move on down the line. Okay, so that's behavior that we expect to see in the waveguide. Let's take a look at the second mode. So it turns out that the next mode has a structure which is given like this, where we see constant variability in the y direction, and we have one cycle of a sine wave. So we go from 0, maximum negative, back to 0, maximum positive, back to 0. So we recognize this as the TE20 mode. We would expect to have x-directed magnetic fields that have the same sinusoidal shape, and we see that. The amplitudes are indicated here as being lower, which is really just an artifact of the way that the computation is done. Right? Now notice when I allow these fields to animate, I've got both x components and z components that are going into and out of the page. Right? And those two field components together demonstrate to us that I'm dealing with a TE mode because I've got a z component of my magnetic field. Let's take a look at what the third mode is. The third mode looks just like the TE10 mode, except it's pointed in the opposite direction. So now I have no variability in the x direction, and I have a single cycle, half cycle of a sine wave in the y direction, so we recognize this as the TE01 mode. When I come back here to my field equations, right, I've got, if I have m equals 0, n equals 1, this term goes to 1. This becomes cosine pi y over b. Okay. And the y component of the field now varies like the y component of the field is 0, the x component of the field varies like a cosine, right? Because I have m equals 0, n equals 1. And so the polarization state is actually rotated. Instead of having e sub y and no e sub x, I've got e sub x and no e sub y. And we see that borne out in the mode. We can go up to the higher order modes. So take a look at the next mode, and this is a mode where now I see that I've got electric field pointing in this direction, this direction. Let's animate it and see what happens. Okay, so I've got some interesting field distributions here. Let's take a look at the magnetic field that goes with it. Right, so that's one of the 1-1 modes that I'm seeing there. Right, where the electric field goes from maximum positive through 0 to maximum negative. This looks like it is a TE11 mode because the H field has a Z component. Right? There should be a TM11 mode. Right? And now what we see here is a circulating magnetic field. Freeze that. Notice the H field is going, at this point in time, it's rotating in a clockwise fashion. I wait 180 degrees, and now it's rotating in a counterclockwise fashion. But now H is circulating around, and this, since I have this rotating H, I expect to have a Z component of the electric field. So we look at the electric field for mode 5, and we see, lo and behold, I've got a very strong Z component of the electric field in the port. Right? When I freeze it, I see that I've also got, it's hard to tell, right? But I've also got electric field that's pointing radially inwards in that mode. The last thing I want to take a look at here in CST Microwave Studio is I want to take a look and see if we can understand a little bit about cutoff frequency. The way I'm going to do that is I'm going to come in here and I'm going to look at the S parameters. Now when you run a simulation like this, your S parameters in CST Microwave Studio, you get this big long laundry list of S parameters. And what's going on here is this S parameter is the S11, and let me take a look at the S12. I'm sorry, the S21. This is the S21, and in parentheses it tells you which mode you're coupling to. So this is the signal at port 2 in mode 1 due to an excitation at port 1 in mode 1. And what we see here is that below 4 gigahertz, I have no signal making it down through my line. But at 4 gigahertz, my S21 goes to 0 dB. What that means is that below 4 gigahertz, this mode is cut off, and at 4 gigahertz or just below 4 gigahertz, this mode turns on. And this comes back to our dispersion diagram. This corresponds in the lowest order mode to a cutoff frequency right around 4 gigahertz. Okay? Let's take a look at what the next mode is. So now I can look at S21 for the second mode. So I'll come down here, S21 in the second mode, and we see that it's cut off at around 7 gigahertz. Right, and recall the second mode that CST Microwave Studio computed was actually the TE20 mode. Okay. We have a full cycle of a sine wave in the x direction, no variability in the y direction. So this TE20 mode we saw had a cutoff frequency of S2212. Oops, I don't want S1, I want S2. There we go. Has a cutoff frequency just below 8 gigahertz. And that corresponds to the 20 mode that we see here, where the cutoff frequency is somewhere between 7 and 8 gigahertz. As we've got in this case here. Let's take a look at the third mode. Right, so the propagation characteristics on the third mode, so that would be S2313, has exactly the same dispersion diagram. Right? Which means it has exactly the same cutoff frequency and exactly the same propagation characteristics. And you should be able to work out the fact that that's not surprising for our particular values of A and B. Because A is equal to twice B, the 20 mode and the 01 mode are going to have the same cutoff frequency and the same dispersion characteristics. If I want to go up to the fifth mode, which was that TM11 mode that we were looking at, I want to look at S2. S25, S1, S2515, which is down here. S2515, we can see that I have a cutoff frequency that turns on here around 9 gigahertz or a bit below 9 gigahertz. And so CST Microwave Studio allows us to determine the frequencies at which the mode turns on by looking at the S21, looking at the S21 as a function of frequency. Okay. So that gives you a feeling, a few different ways of looking at the mode structure and understanding how those fields are distributed. And that becomes important in a number of reasons. It becomes important when you're trying to do coupling between two waveguides. It becomes important when you're trying to radiate out the end of a waveguide. It becomes important when you have parasitics that can possibly interact with your waveguide and create signals that you don't want in them. And these are all potential areas where understanding the mode structure can be of benefit. So to conclude the tutorial topics, we're going to ask you to sketch the field lines for some of the port modes so you can get a feel for mode shape. Compute the cutoff frequencies and look at the dispersion diagrams. Understand where you want to operate. And the last thing what I didn't look at in CST Studio is mode impedances. So CST will also allow us to take a look at the mode impedances here in the one-dimensional parameters. So I'll close that and open up reference impedance. And I can take a look at the Z reference for each of these modes in the port. So what we see here for the lowest order mode, which was that TE10 mode, we can see that the reference impedance is 0, right, because I don't have any propagation. And then it jumps up to infinity right at cutoff, and then it asymptotes down. And let's see what value this asymptotes down to. Let's put measure lines on. And that will asymptote down to a value of 367 ohms. Actually, probably 377 ohms, right? Well, 377 ohms happens to be equal to the impedance of free space, right? So when I take the square root of mu naught over epsilon naught, I get 120 pi. Right? So the square root of, you can work that on your own. Square root of mu naught over epsilon naught gives you 377 ohms, and that's the impedance of free space. If I take a look at the second mode, which we'll recall was a TE mode, we also see its impedance goes to infinity and then drops down to 377 ohms. The third mode, which was the TE01 mode, this behavior. Let's go back to that fifth mode. The fifth mode, recall, was a TM mode. And that TM mode has an impedance of 0 until cutoff, and then it starts to increase, and it too will asymptote to 377 ohms if I were to run this out to a higher frequency. And so that lets us see that I can take a look at the mode impedances. This is clearly a TE mode. There's a TM mode because it starts at 0. The sixth mode is a TE mode. The seventh mode is a TM mode. All right, let's take a look at what the fields look like in that seventh mode. We see that this corresponds to the TM21 mode, where I've got an oscillation. So I've actually got 2 loops here. If I stop it, stop length filter maximum, here I've got a circulation that is clockwise, and over here I've got a circulation that's counterclockwise on the other half. So this is the TM21 mode, and its cutoff frequency corresponded to cutoff frequency here of around 10.5 gigahertz. Okay, so those are some of the things that we're going to ask you to look at in the tutorial for this particular lecture. Understanding how the mode shapes work, how that relates to dispersion diagrams, and how that relates to mode impedances.